Okay, so hello everyone, we are group 3 and we are going to talk about the instant neural graphics primitives, lightning fast nerve and more. This is the outline of this presentation. Before getting into our main paper, we would like to first talk about the concept of nerve. So nerve is the first paper to represent a 3D scenes in a neural radius fields and use MLP to encode the entire scenes. This text code is called novel field synthesis. Given a bunch of 2D images, each image with corresponding camera poses, nerve wants to train an MLP so that this MLP can encode the entire scenes. After training, this MLP can be used to render a new views of the scenes. For nerve to render a 2D image, we need to shoot an array for every pixel on the image, as we'll query several sample points along the array. For each sample point, it will correspond to a 5D factors, its 3D position, and its Fourier direction. And the MLP take these 5D inputs and map it into color and density of the given sample points. After getting the color and density of the sample points along the array, we perform fiber rendering and get the final color. And to optimize this MLP, we render the 2D image by fiber rendering, like render a whole image, and by fiber rendering and use L2 loads with the ground truth, and it will propagate to the MLP using gradient descent method and optimize this MLP. And after training, we can use this MLP to render novel field synthesis with different camera pose. Okay, this is the demo of nerve. And when it first published, it is the SOTA model for novel field synthesis and surpass other methods by a lot. As you can see in this video, and its performance is actually surpass other methods by really a lot. Okay, however, nerve is very slow. It takes hours for optimizing the scenes. Why nerve is so slow? First, because it encodes the entire scenes directly in MLP without additional data structures. Thus, encode the spatial information in MLP may take additional time. Second, when performing file rendering, we need to sample a lot of points along the array, and the number of rays is equal to the number of pixels in the rendered images. This will also make the spend a lot of time when rendering an images. And some methods try to tackle the both issue by employing different data structures, like an SVF and DGO combine voxels and nerve, and plane arteries combine arteries and nerve, and plane voxel directly discard MLP, and use only sparse voxel grid and spherical harmonics to encode the entire scenes. And Instant-NGP, which we will talk today, combine nerve and multi-resolution hash grid, and this method achieves SOTA performance and training speed. Let's talk about the key idea of Instant-NGP. The full name of Instant-NGP is Instant Neural Graphics Primitives with a multi-resolution hash encoding. The first author of Instant-NGP is Thomas Munder. And this is the teaser image of Instant-NGP. As we can see in the fourth row, Instant-NGP can quickly reconstruct the Lego model in only 1 minute with very high quality, as shown as this image. This is not possible by previous method. None of them can reconstruct these high quality scenes in such a short time. Besides nerve, Instant-NGP can be used in many other tasks like gigapixel image approximation, SDF, and NDC, which we will talk about later. This is the main pipeline of Instant-NGP. So the first step is to encode the position X by the multi-resolution hash encoding. And after we get the feature factors from this hash encoding, we will concatenate it other inputs and set this whole encoding factors into the MLP. And this MLP is actually a Fourier fused neural network, which we will talk about later. And this MLP will output different output depends on the task you want to perform. For nerve, it will output density and color, and for SDF, it will output the distance to the closest surface. So the key idea of Instant-NGP is first, Fourier fused neural networks. And the Fourier fuse means the entire neural network can be implemented as a single GPU kernel, and thus less memory overhead. Notice that the Fourier fuse neural network are smaller because it needs to fit into the GPU cache for every GPU core. And second is multi-resolution hash encoding. And this hash encoding achieving good approximation despite we have a smaller MLP. And third is task-specific GPU implementation. And for example, the author of Instant-NGPs have designed several algorithms to reduce the number of query needs for each array in the nerve task. And let's discuss about what is the benefit of a smaller neural networks. And let's first look at this vanilla MLP. Suppose each block contains 2 layers, and each layers with m neurons. And this rectangle represents the matrix of when we have an input have size that in this batch size. And we have L block for this MLP. And when running this MLP in GPU, we are essentially performing matrix multiplications. And after multiplication, the GPU will write the result to its RAM. And after that, we will read the result from the RAM again for the next layer, and so on and so on. And because of this will cause a lot of memory overhead. And because matrix multiplication can be done in parallel, thus memory overhead becomes the bottleneck of this MLP. So let's dive into the block of MLP. And suppose we design a small MLP with the number of layers is between 2 and 6, and the number of neuron M is between 32 and 128. This is much smaller compared to the original implementation. Next, let's calculate the batch size for rendering a 2D images. And for rendering an image with width and height equal to 256, it has in total 256 times 256 frames emitted from the camera. And suppose for each ray, we sample 100 points, thus the batch size equal to around 6 million, which is make the matrix in LP very wide but short. Because of this, the offer of Instant-NGP splits the single wide MLP into multiple MLP along the batch size dimension. Like this split the batch size dimension into many small neural networks. And in this way, each small MLP can fit in one GPU core's cache, and one GPU core can do the computation from top to bottom. And in this way, we don't need to store the data. We don't need to write the data into RAM and read it again. Thus, the memory overhead of this small MLP become very less, and thus we will save all the memory bandwidth and reduce the memory overhead. And this kind of MLP is called the full-refused neural networks. Thus, the entire neural networks implemented a single GPU kernel, which create full-refused neural networks. This is only possible when the neural networks is small enough to fit into the GPU caches. And this figure shows the throughput of training and inference for different batch size. As we can see, the speed up of full-refused neural networks over TensorFlow is around 5 to 10 times. And the solid line represents 16 neurons wide MLP, and the dashed line represents 128 neuron weights. As you can see, in both scenarios, the full-refused neural networks outperform the naive TensorFlow implementation very much. So next, after we going through the small neural networks, let's talk about the hybrid data structures. And to be more specific, this data structure in Instant-NGP is called multi-resolution hash encoding. And this hash encoding makes the small MLP able to reconstruct a small scenes despite has a smaller neural network architectures. In the original nerve, it introduced positional encoding, encode the position and directions by sine and cosine function, which make MLP able to catch high frequency detail. And similarly, in Instant-NGP, it also introduced a novel encoding method, and this method is called multi-resolution hash encoding. So the hash encoding used in Instant-NGP consists of various levels of resolution, and each resolution will correspond to a hash table with same size t, and each entries of hash table will store feature factors with size f. So the f is the feature factor dimension, and the t is the size of the hash table for each level of the resolution. And in this figure, we will look at a simple example where t equals to 8, the hash table size is equal to 8, and the number of the level equals to 2. So there's only 2 hash table, and the dimension of feature factors is also equal to 2. That is only 2 block in the one entries. And also in this case, n0 is equal to 2 because we only have the n0 is a 2 by 2 hash grid, and the n1 is equal to 3 because in the rate like this 3 by 3 hash grid, which gives us the group factors of b of 1.5. Okay, so how we use this hash table and hash encoding for given position x, we will first calculate its relative position in the grid, and this is actually very easy and can be done by simple multiplication. And we will query its nearest grid points. In this case, for each label, we will query 4 points. And for 3D case, we should query 8 points because we are living in a 3D cube. So it should be 8 points. But in this case, we have only 2 degrees, so it's only 4 points. Anyway, in this example, we will query 8 points. In total, 4 points for each label, like 1, 2, 3, 4, 5, 6, 7, 8, like this 8 points. And calculate its spatial hash value based on this equation. And the offer of Instant-NGP set pi 1 to 1 to achieve high cache coherence, and pi 2 and pi 3 are random large prime numbers. So after calculating all its hash value, we will look up the hash table. Like for example, the hash value for this grid point is 2, so we will look at these feature factors, and this is 0, so we look at these feature factors, and so on. And next we will apply the nearness interpolation for the linear interpolation for the nearest neighbors. Like we will interpolate by these 4 value and to get the value feature factors for this label. And after we get the feature factors for each label, we will concatenate the feature factors of each label. Like there are 2 labels, so we have 2 feature factors here, and also we will also concatenate other inputs into these whole factors. And yeah, and these other inputs often consist of like pure reduction or spherical harmonics. Yeah, and the resulting factors is the input for the full-refused NLP. Yeah, it's basically the basic idea of the multi-resolution hash encoding. So it just use a multi-resolution hash grid and a hash table and linear interpolation And after linear interpolation, you'll concatenate the feature factor together, and this concatenated vector will be the final input to the MLP. And the previous illustration is a very simple example. And in real-world application, Instant-NGP uses the value in this table for every parameters. The number of level L is fixed to 16, and the dimension for each feature factor stored in the hash table is also fixed to 2. This is the empirical results from thorough experiments, which we will discuss about later. The only two parameters that are suggested to be tuned in is the size of the hash table T and the finest resolution max. And we know that if the number of entries is smaller than the number of grid, hash collision will occur. Hash collision means that different spatial location mapped to the same hash table entries. This can be troublesome because different spatial locations should have different feature factors. So how is the NGP handle this issue? And actually, Instant-NGP doesn't explicitly handle hash collision issue because of the design of hash function. Hash collision should have happen pseudo randomly scattered across the space. And because the hash grid has multiple levels, it's also unlikely the hash collision occurs simultaneously at every level for given positions. And also, we take nerve as an example. We know that a point on a visible surface will contribute strongly to the images, thus causing large changes to the corresponding table entries. And in the contrary, a point in empty space that hashed to the same entry will have much smaller weights. So in conclusion, the gradient descent optimization will naturally make every entry reflect to the needs of higher weighted points. And this is actually how Instant-NGP handle hash collision implicitly without any tracing pointer and like this and other methods. So let's talk about the final key idea of Instant-NGP. And it is further optimized, which further optimize the entire algorithm. And let's take nerve and as an example. The offer of Instant-NGP first make the stepping of the sampling grow exponentially when the size is large, and this will make the sample point become lesser. And they also introduce an occupancy grid, and this grid will be updated during training. And with this grid, we can easily skip empty space and occluding region so that we don't want to sample this kind of area. We also want to sample the area that close to the surface. So when performing the file rendering with the occupancy grid, we can easily decrease the number of queries for the MLP. So these two ways is for decrease the number of queries needed for the MLP. So the three key ideas make Instant-NGP extremely fast. It only takes about 1 minute to optimize a scene and achieve around 100 times speed up over existing nerve methods. And Instant-NGP is implemented fully in CUDA, which makes it super fast. And the free refused MLP is from a framework called CUDA, which is developed by NVIDIA. And this CUDA provides an API, and which can be used in PyTorch. And their implementation speed up is about 10 times faster compared to the naive PyTorch implementations. Now let's discuss about downstream tasks of Instant-NGP. Gigapixel image approximation, side-distance function, and neural radiance field. Radiance and density fields are the main three downstream tasks of Instant-NGP. And for GIA and SDF, the experiment conducted later will have MLP with 2 hidden layers with width of 64 neurons. And the gigapixel image approximation wants to use Instant-NGP to feed an extremely high resolution images, which will have lower memory usage than the original image. The below figure uses Instant-NGP to feed these gigapixel images with different hash table size T, and when T is set to the power of 22, the Instant-NGP achieves PSNR of 29.8 dB with only 3.4% of the degrees of freedom than original images. Next is side-distance functions. Side-distance function maps a position x to a scalar, which indicates the distance between the position x and the nearest surfaces. Therefore, the surface should lie on both points with its SDF equals to 0, and thus this function can be used to model the surface of given things or objects. And the last one is nerve. Unlike GIN and SDF, it follows the setting of the original nerve, which uses 2 MLP to predict the density and color. And the density MLP takes the hash encoding and outputs 16 values, and the first of them are treated as density. And the color MLP takes these 16 values and the spherical harmonics and map them to RGB. And the density MLP has 1 hidden layer, and the color MLP has 2 hidden layers. All of them are 64 neurons wide. Let's talk about our project goals. We want to use GUI to run GIA, SDF, and nerve experiments. And also, in the original paper, the author only takes on nerve syntactic datasets. So we want to take Instant-NGP on an unbounded dataset called Vector 360 dataset. This dataset is unbounded. And also, we want to test the performance with different hash table size T. And lastly, we want to compare Instant-NGP with the extincting method, including 3D Gaussian stacking. Okay, let's talk about our experiments. So first, let's discuss about how the authors of Instant-NGP decide the size of the hash table. They conducted different experiments on GIA, SDF, and nerve. And for this test, set t to 2 to the power of 19 yields the best result in terms of training time and quality. As you can see, this t is on the upper left of this diagram for each task. So that it's worth to mention that the performance cliff is feasible at t greater than 2 to the power of 19. Like here, they have the performance cliff. This is because the test RTS3 or 9.0 GPU become oversubscribed. The author conducted experiment to find the best L and F, and it turns out the best configuration is F equals to 2 and L equals to 16. Like it is the most upper left points. So let's talk about our own experiment. So the experiment is conducted by the official codebase here. And the official codebase has provided a convenient UI, making it easy to navigate the scenes or the model, all the 3D models. And we will text on the three tags: gigapixel image approximation, SDF, and NERF. For gigapixel image approximation, we use an 1.2 gigapixel per norma of Shibuya in Tokyo, Japan. And this is the link to these images. As we can see, the Instant-NGP can quickly fit this huge panorama in very short time. And this demo is not speed up. Okay, let's look at the next example. Let's talk about SDF. For SDF, we download the OBJ mesh file from internet and test if Instant-NGP is capable to reconstruct the 3D model using SDF. This is a model of a man, and as we can see, Instant-NGP can quickly reconstruct this man model in just around 5 seconds. This is the original model file we download from the internet. And next example is also SDF. This is for a model of a room. As you can see, with the SDF, the Instant-NGP quickly converge, and this is the original OBJ mesh file downloaded from internet, which is very close to the actual reconstruct by Instant-NGP. Okay, so the next experiment is in NERF. As we mentioned earlier, the original paper only tests on NERF synthetic datasets, which consists of 8 synthetic objects. And in this project, we want to test if Instant-NGP is able to reconstruct among these things. Therefore, we use MIPNER 360 datasets, which contains 9 among these things with complex central object or area and a detailed background. And the camera pose is calculated by callback. And we first show the results of the Lego model from the NERF synthetic dataset. As we can see, the Instant-NGP quickly converge and reconstruct a very faithfully 3D models of this Lego. We have very fine detail on this model. Let's look at for a MIPNER 360 datasets, we download the garden scenes, and because the Instant-NGP define axis line, bounding box, or AABB for each scenes, and the default size of AABB is too small for MIPNER 360 datasets, so we set the scale to 64, and the result is like this video. And this base is the original AABB size, and as we can see, because the scene is too large, so the background is stick to the unit cube demonstrated in this video. So we make the scale bigger, and after we set the scale to a bigger AABB, the background will be normally displayed in the bounding box. And as we can see, Instant-NGP is also capable to reconstruct the background of these things. This means that the Instant-NGP can reconstruct bounding things as well. This is the PSNR result for different methods and datasets. And for non-synthetic dataset, we compare Instant-NGP with NERF, original NERF, and an SVF. And Instant-NGP used only 5 minutes to achieve PSNR of 32.99 dB, which is very close to MIPNER PSNR 33 and 30.09 dB. But MIPNER takes hours for optimizing the scenes. And for MIPNER 360 datasets, we compare Instant-NGP with 3D Gaussian splatting, Planexo, and MIPNER 360. And with larger AABB, the Instant-NGP can reconstruct the scenes with PSNR 24.08 dB. And the table size here are set to 2 to the power of 21. And we also conducted the experiment with different hash datasets with fixed iteration of 2000. As we can see, the PSNR does increase when we increase the hash table size, but the training time is also increased, like here. And we also observe the performance cliff when t is larger than 2 to the power of 19, which is consistent with the original paper. Lastly, is our conclusion. First, the Instant-NGP remains the fastest method to 3D reconstruction. Although the rendering time is slower than 3D GS, the training time is still way faster than 3D GS. Second, Instant-NGP combines advanced approaches for optimal performance, including fully fused neural network and multi-resolution hash encoding. And most importantly, both of them are task agnostic, as they can effectively apply on different tasks like GIA, SDF, and NERF. The third is we can know that proper analysis and identification of bottlenecks are crucial for optimization. And lastly, implementing the entire framework in CUDA significantly enhance the performance. This is also can be observed for the implementation of 3D GS. And this is our reference. Thanks.